Okay, guys, we're gonna do I'm gonna do an example here from 7.6. It's in the end of the section, one of the exercises, number 21. And so this is gonna be an exercise in modeling something from the real world using our sinusoidal functions. So let me write down the gist of the problem. So we've got a Ferris wheel with a, let's see, 20 meter diameter. So I'm just going to write a 10 meter radius. We know that it tells us that the bottom of the wheel is 2 meters above ground. And what else does it tell us? That one revolution takes 6 minutes. Okay, so that's our situation. The question they want to know is how much time is spent above 13 meters. Okay, so imagine we're going to imagine somebody getting on at the bottom. They're going to do one full rotation. We know that takes 6 minutes. We want to know how many of those minutes. It tells us to do it in minutes and seconds. How much time is it above 13 meters? So I'm going to start with a picture just to have an idea of what's happening here. So I've got my Ferris wheel. I know it's sitting above the ground. I'll call that the center of it. And let's just mark off some of these heights off to the side. So for instance, I know the bottom of it is at 2 meters. The radius is 10 meters, so that center should be 10 meters above the bottom, so at 12 meters, and then the top would be another 10 meters above that, right? So that's a reasonable picture to start with. Our ideas, remember, we're going to think about there's a person getting on here, this is going to go around, and we want to know how much time, so 13 meters would be somewhere over here, how much time is spent above this line, this 13 meter line, right? And just looking at the picture, we can make an estimate. It looks like, well, certainly 13 meters is above half, so less than half the trip should be spent above there. So a bit less than 3 minutes is what we should be looking for in our head, right? So we'll just kind of keep that in the background. So how do we go about figuring this out? So I think the way I'm going to approach it, I'm going to come up with a function that tells me the height of somebody who gets on here. I'll take, so let me write it and then I'll say what everything is, what I've done. I think that'll be easier. So cosine of bt minus c plus d. So here's the form of the function I want. So this is going to be a function h. Our input is t. That's going to be time, where time I'm going to take to be minutes after the ride starts. So at t equals 0, my person is at the bottom of the Ferris wheel. And as time goes on, as minutes pass, I want this function to be spitting out values that represent the height of that person at that time. Okay? So I've chosen cosine. First of all, I've chosen a sinusoidal function because I've got a situation here where if this ride were to keep going around, they would repeat, and we know we can use sines and cosines to describe things that repeat, not to mention the fact that it's in a circle, so that gives us an indication that we know how closely related to circles sines and cosines are. I could have chosen sine or cosine. I arbitrarily chose cosine, and I'm going to go with that. So my job now is to find the values of these constants, right? This is pretty similar to the exercise I asked you guys to do on the, I can't recall now if it was the written homework or the quiz. But in any event, this is a good exercise in modeling. So let's just go through the constants. I'm going to start with d. A and d usually are pretty easy to get. Remember, d is related to our midline. In this sense, the midline is going to be y equals d, right? In other words, d is the point halfway, d is the value halfway between the maximum value and the minimum value that our function is going to take on, right? We've discussed this a few sections back. Well, this is clear from the picture. The highest height our person is going to hit is 22 meters. The lowest height is 2 meters. We already know exactly what's in the middle. It's the center of this circle at 12 meters. So this D should be 12. Okay, so I'm just going to box that because I know I'm going to need it later. A, remember, is related to the amplitude. The absolute value of A is the amplitude. And the amplitude, recall, is the distance from the midline our function gets, right, in either direction. So in this case, we might get 10 meters above or 10 meters below, but in either case, we're going for 10. Now, because of that absolute value, we can choose A to be positive or negative. I almost always just choose it positive, just to keep things simple. So I'll take A equals 10. And then the next one I'll get will be B. B is related to the period, right? Period is 2 pi over B. Well, we already know what the period is. The period is the amount of time it takes to do one complete cycle. And in this case, that's given. We know our period is 6 minutes. So this equation becomes 6 equals 2 pi over B. Multiply B to both sides, divide by 6, and I get pi over 3 for B. Okay? So let's box that one. Now, at this point, depending on how much practice you had with these, there's a few ways to go about figuring out the last bit of this. I'm going to draw a sketch before I find C. Right? So at this point, without C, which we know is related to the phase shift, I have a function that looks like this. D was 12. Okay, let's sketch a quick graph of this. I'm not going to try to be super perfect with it, but I want to get an idea of what it's going to do. So I'll just mark off. There's a maximum. There's a maximum. There's a minimum. Here's our midline. And let's also just mark off cosine in terms of period. So there's a period. Here's a half period. And here's quarter periods. Cosine typically starts at starts at its maximum. After a quarter period, it hits the midline. After half a period, it's at the minimum. At 3/4 of a period, it's back to the midline. And after a full period, it's at top. The same thing happens in this direction. Let's just sketch this in both ways, right? Here's a quarter period, half a period, 3/4. That's a little too high, but you get the idea. So let me sketch that really quick. We're getting a picture. So this drawing is not totally accurate, but we get a general idea of what this cosine, as we have it so far, how it looks. Okay. But there's a problem with this, right? According to this graph, remember this, the y values of this line represent the height of our Ferris wheel rider. At t equals 0 along the y-axis, this graph gives us our rider being on the top, as if they got on the top. But we know they should be getting on at their minimum. In other words, I want to shift this graph so instead of being at t equals 0 being a maximum, I could move this point backwards, or I'm going to actually imagine moving this point forward so that we get this, right? If I shift this and the distance I'm shifting it, this is half of a period, I want to shift it half a period forward. And that will give us a function that starts at the bottom, in half a period gets to the top, and in the second half is back to the bottom, right? And that would be, and so this is our 6 minute period, okay? So that tells me the phase shift. The phase shift, remember it's the distance I'm shifting here, is half a period, which we know to be 3 minutes, okay? So, right, a period is 6 minutes, so half a period is 3. But remember, the phase shift is equal to C over B, so these two things must be equal. In other words, C over B, and I'm going to put in the value for B, which is right here, so C over pi over 3 is equal to 3, right? C over B equals the phase shift. C over pi over 3 equals B. Multiply both sides by pi over 3, and I get C equals pi. Okay? So this gives me h of t. All right, I've circled all or boxed all of the relevant values. I'm just plugging them into this formula. So I've got h of t equals 10 cosine pi over 3t minus pi plus 12. Okay. Now, you could go ahead and graph that on something like Desmos if you want to get a picture of it. You should probably practice graphing it by hand as well. But it should look like something like this, depending on the scale. We get this dotted line, right? Something that begins at 0, or at the minimum, climbs to the top in half a period, and then comes back to the bottom over one full period. Okay? All right. So let's start a new page here. Let me copy this function, because we haven't answered the question yet. Right? This is what I asked you to do on your written assignment, which was to find a function to model, in that case, the heights, the distances that hands on a clock were from a ceiling. This is a similar idea. But this question actually asks us to do something different. So let me sketch this again. Maximum, minimum, midline. Let's just put one period out here. Let's actually do it with numbers. We know a period is 6. Half a period will be 3. Quarter period, 3/4 of a period. Of course, we're starting on the bottom. Quarter period, we're at the midline. Halfway, we should be at the top. 3/4, we're here. And by a full period, we're back to the bottom. And we get some kind of picture that looks like this. Okay. Now, remember, this midline is y equals 12. The question asks us, when is our rider above 13? So I've drawn a dashed line above 12. What we need to find out is how much time passes. Here's the moment that our rider is at 13. So we want to know how much time elapses from here, where they first go above, to back below, right? And again, similar idea we had before when we looked at this picture. Above 13 looks like it takes just a little bit less than half a period, because it's about halfway around the circle, just a little less than halfway. It's the same thing here. From this point and this point, that's a half a period. We're just slightly inside that. So again, my estimate in my head is that we should expect a number a little less than 3. Okay? So let's think about how we can accomplish this, right? Well, I want to just find out what these intersection points are. In other words, I want to know, when does h of t equal 13, right? What t values give me 13? Okay. So now we have an algebra problem to solve. So we get minus 12 minus 12. So I've got 10 cosine pi over 3 minus pi equals 1. Let's divide by 10. I get cosine of pi over 3. Oops, I forgot my t in here. Excuse me. Minus pi equals 1/10. And now we can take our inverse cosine. So we'll get pi over 3t minus pi equals inverse cosine of 0.1. And I'm going to calculate this in a moment. This is just some number that my calculator can handle. This isn't some known value as far as I can tell. So this will be a calculator issue. I'll add pi. I get t equals pi plus cosine inverse of 0.1. And then multiply both sides by the reciprocal, or 3 over pi. And this gives me a decimal approximation. Let's see, I had this computed. This turns out to be, I'm going to round it to the nearest tenth. I get 4.4 minutes, right? So what does this number represent? This is one of the intersection points, right? Well, it's actually pretty clear which one it is. We know here's we know there's two possible intersection points. We know cosine can only give us one. I mean, there's actually an infinite if we imagine this ride going on and on forever. But in our little picture, there was two possibilities. Inverse cosine will only give us one of them. It gave us 4.4 minutes, which has got to be this intersection point right here. Okay? So we need to use that to figure out what this intersection point is, right? And a pretty easy way to do it is to notice, so here's our period. There's a lot of symmetry in the cosine graph. From here to here should be the same distance from here to here, or the same amount of time, right? Here's this is right in the middle. They're symmetric about this peak. And so this distance here from t equals 4.4 to 6 minutes, well, that's easy enough to calculate. 6 minus 4.4 will give us 1.6, right? This is 1.6 minutes. And so this should also be 1.6 minutes. Okay? So that means our two intersection points, right? So we first go above 13 meters after 1.6 minutes until 4.4 minutes, right? That's when we go back below. So how much time is that? How much time elapses will just be 4.4 minus 1.6 gives me 2.8 minutes. Okay? Which, this doesn't prove that I'm right, but is exactly what we estimated in the beginning. It should be a little bit less than half a period, or 2.8 minutes. Now, the question asked us to give our answer in minutes and seconds. So I want to change this decimal, the 0.8 part of it, 0.8 minutes. We can convert this to seconds by just noting that 60 seconds is equal to 1 minute. Our units here cancel. We get 0.8 times 60 equals 48 seconds. So our rider will spend 2 minutes, 48 seconds above 13 meters. Okay?